Assalamualaikum and greetings everyone. Today's topic is on applications of double integrals. As you can see, we have used double integrals to find area of a region, and we can also find volume of a solid using double integrals. Apart from those two, we can also use double integrals to find moments and center of gravity or center of mass of a lamina. Before we go to a lamina, let's look at a solid in 3D first. If you have a solid that has mass m, so m here represent mass of a solid, and volume v, so v is volume of a solid, and the mass is uniformly distributed throughout the solid, we say that the solid is homogeneous. So homogeneous is for solid that has uniformly distributed mass throughout the solid. The mass density, denoted by delta, is defined as, so density is equal to mass divided by volume. So m here is for mass, v is for volume, delta is for density. So rearrange the formula here. We can get mass of a solid is equal to density times volume. So mass of a solid is density times volume. Okay, now let's look at lamina. What is lamina? Now, if we consider an idealized flat object that is sufficiently thin, it can be regarded as a two-dimensional solid, then that type of object is called lamina. So lamina is really a two-dimensional object, so 2D object. Because it is so thin, we can regard it as a 2D object. Okay, for a lamina, the density and the mass of a lamina is given as that. So now, density of a lamina is equal to mass divided by area. Remember, a lamina is a 2D object, so instead of a volume, it has area. So density is mass divided by area, or we can rearrange this. Mass is equal to density times area. So A here is for area. Okay, now the first theorem. If the density function delta of a lamina R, so lamina is 2D, so we have region instead of volume, is continuous, then its mass m is given by, so here we have the first formula that you need to know. Mass of a lamina is equal to density integrate over region R. So if the integrand here represents density of a lamina, then integration of density is mass of a lamina. Okay, so that's the first formula where you can use double integral to find mass of a lamina if the integrand represents density of a lamina. Okay, now let's look at more formula. Next is the center of mass or center of gravity of a lamina. So here, remember your lamina is a two-dimensional object. So you have a region here. So we have a region R. Okay. For density, for center of gravity, you have a point. So let's say this is a point x bar, y bar. Okay. So this is x bar, and this is y bar. So for center of gravity, if you put a pin on this point, then your lamina will be at an equilibrium point. It will be stable, okay, equilibrium point. So this is a point called the center of gravity or center of mass of a lamina. So now let's look at how to get this point x bar, y bar. Okay, we have a formula for that. So for center of mass, the center of gravity is equal to, so here we have x bar and here we have y bar. So for x bar is equal to, so we have x times density integrate over region R divided by density integrate over region R. For y bar is equal to y times density integrate over region R divided by density integrate over region R. So the numerator here, we can denote that as, so the denominator here is, numerator, x times density. So x times density integrate over region R is what we call moment with respect to the y-axis, denoted by my. Moment with respect to the x-axis is denoted by mx is equal to y times density integrate over region R. So for x bar and y bar, we can simplify this as this is really my, and in the denominator that's just mass. So for y bar, this is mx, moment of inertia, moment with respect to the x-axis, and in the denominator we have this is mass. So density integral over region R is mass. Okay, so two formula for you. First one is mass of a lamina, which is this one, and then now we have formula to find center of gravity, x bar and y bar. Okay, more formula. Next is what we call the centroid. Okay, what is centroid? If the density of a lamina is constant, so delta, so that density is represented as delta, so delta is density. If the density of lamina is constant, meaning that it doesn't depend on x and y, it's always the same, a constant, then the center of mass is called centroid. So centroid is just another name for center of gravity when the density is constant. Okay, so it's still x bar, y bar. Okay, so remember this is the formula. This is the formula for x bar. Okay, but if the density here is constant, then we can write it down as k. Let's say k represent a constant. So this is the original formula. X times the density. Density now is a constant. And in the denominator, we have density integral over region R. Now density is a constant, so we can write it this way. Now remember, we have a constant k and a constant k in the denominator. We can write the constant before the integration. And we can do the same thing in the denominator. So a constant k divided by the same constant k, that is equal to 1. So the formula can be reduced to this. And you can see that now the denominator is just dA integrate over region R, which is really area of region R. And in the numerator, we have x integrate over region R. So now the formula for x bar will be reduced to this. Excuse me. And the formula for y bar will be reduced to that. So this is another formula for you to remember, which is the centroid. So centroid is just a center of gravity for a lamina when the density is a constant. So when the density is constant, the formula for x bar and y bar will be reduced to this. Okay, so that is centroid. So now so far you have three formula: mass, center of gravity, and then the centroid. And the last formula for you to know is moments of inertia, or it's also called second moments, but usually we call it moments of inertia. Okay, another theorem. If the density is delta xy continuous on region R, where region R is really where your lamina lies on, then we have 3 more terms that you need to know. One is called moment of inertia with respect to the x-axis. So here we have Ix. The integral now is y squared density integral of region R. And another term that you need to know is moment of inertia with respect to the y-axis. We have Iy. The integral now is x squared times density integral of region R. And another term is moment of inertia with respect to the origin, Io. The integrand is x squared plus y squared, everything multiplied with density, delta, and then integrate over region R. And this is also moment of inertia with respect to the origin is also equal to Iy plus Ix. Because if you write this using two double integrals, then it's just really Iy times plus Ix. Okay, because x squared delta is Iy, y squared delta is Ix. Okay, so those are applications of double integrals where we can use it to find moment of inertia. Centroid, which is just the center of gravity when the density is constant, and here we have center of gravity, and the most important is mass. Okay, and to evaluate this, it's just evaluating double integrals. And for double integrals, as you know, we have two coordinates. One is Cartesian and the other is polar. So which one to choose depends on your region R. So if your region R involves circles, cardioid, then the good coordinates to use would be to use polar coordinates. But if your region R consists of straight lines, parabola, then the good coordinates to use would be the Cartesian coordinates. Okay, so how to find the limits of Cartesian coordinates and polar coordinates, we've covered that in the previous videos, but I will show you examples of finding moments, center of gravity, moment of inertia in our life class. Thank you.